Our next speaker, I'm very happy to introduce Professor Nicola Tondini. Nicola is an associate professor of structural engineering and structural fire engineering at University of Trento in Italy. Nicola, the floor is yours.
Thank you very much, Thomas, for the invitation and the presentation. Today, I'm going to present some applications of SAFIR in terms of the numerical modeling of steel and steel concrete composite bridges. So, okay, sorry. So this is the outline of my presentation. So I will start with some background on why we do this kind of analysis, and I'm going into the description studies. One is a steel-tied arch bridge, and the other one is a simply supported plated girder bridge. And then there are some conclusions. So I will show you some comparative analysis, and then with different fire scenarios with prescriptive approach and performance-based design. So I start with the motivation. I mean, we have some data about Italy. Of course, you can find in the literature data from other countries, especially from the United States. Here, for example, is the number of total vehicle fires in Italy. See, the source are the fire brigades. You can see this more than about 20,000 per year. And on the right, you can see that in the highways, freeways, there is 20% of this number occurs in the highways, freeways, where there are a lot of overpasses, and sometimes, even though of course the probability of occurrence of a fire under or over a bridge where the structure, for example, is above the road, for example, for an arch, is not as high as in a building, but of course you might have like very high consequences. So here it is an example of this. This is a fire that occurred in Italy in 2018. So there was a road accident underneath a concrete bridge, not very far from Milan. So there was a tanker with flammable liquids that ignited, and then this is what happens just underneath this overpass on the other motorway. So the consequences of this accident was that I mean, after the tests, it was found out that the bridge was not able to withstand the loads anymore, so it was not safe anymore. So there was a demolition part and also a rebuilding of the bridge. So after more than one year, there was a new opening of the overpass. So this, of course, entailed a lot of consequences. First of all, of course, the temporary closure of the infrastructures, longer travel times for the people that live nearby, loss of revenues of the highways because of the closed road for some time in order to put into safety that length, I mean, a part of the highway. Then, of course, decrease of the business revenues and possible company closures. There is I mean, we didn't estimate this, but of course it can happen also, but at the environmental level, that a new bridge had to be rebuilt, and also more pollution due to longer travel times, because there was no shortcut anymore for people, for example, commuting going to work. So this is just an example. There are many examples in the literature. There was also a large fire in the United States end of June of this year. And here there is the project that behind this motivation that was funded, and that is based on the risk analysis and criteria for mitigating the effects of fire on bridges, also supported by Autostrada del Brennero, which is a motorway not very far away from my university. So the objectives are consideration of the vulnerability of the bridges, risk analysis, and also development of possible mitigation strategies. So here, let's go into the modeling of a couple of case studies that can represent overpasses of a highway. The first one on the left is a steel tied arch bridge, and on the right is a bladed for the bridge. So the first one is 65 meters long and almost 15 meters wide. Whereas the other one is 45 meters long and 60 meters wide. So some characteristics about the cross section. Basically, this steel tied arch bridge is an orthotropic steel deck. So basically the concrete slab did not participate to the structural, structural section or the stability of the bridge. So we consider it only as a weight. The properties of the steel grade were like S355, and the hangers were made of a high strength steel 750 megapascal. There were like two traffic lanes, and the arch is in the middle, as you can see, between the two lanes. Here is the first modeling that we performed in SAFIR in terms of the structural model was by means of beam finite element, with Euler-Bernoulli beam elements. These are the cross sections, for example, of the arch, that is the cross section with the void, and also this orthotropic the deck with this section that was simplified, and also the fact that there were some ribs, some stiffness that were also included in a simplified way. Of course, if there is a void, the cavity is very important in this case, above all if the fire is underneath the bridge. Here the load combination that we used basically is self-weight of the structure, permanent loads, and indirect effects due to the fact that due to thermal expansion, the joints that are there to accommodate the normal temperature, seasonal temperatures variation over the year, and can also, this expansion joint can close and then, of course, create some indirect actions. We didn't consider variable loads in the sense that we assumed that when the fire was underneath, for example, the bridge, no cars were on the deck. Interesting is what we applied in order to model the expansion, the effect of the expansion joint. So the expansion, the thermal expansion void was 20 centimeters wide, and we created a particular structure into SAFIR in order to reproduce more realistic boundary conditions, in the sense that typically, you can also in the literature, you can find boundary conditions that are simply supported or like hinged supports. In this case, what we developed, it is with the elements that are within SAFIR, a small structure that is able to reproduce the effect of the expansion joint, and above all, when the expansion of the bridge is such that this thermal expansion joint is closed, and then also it creates some indirect action. So you can see what the way that we have done. So there are some truss elements that have stiffness that's much higher of the stiffness of the deck, and we put also here a spring that with really small stiffness, but it was mainly for convergence reasons. And as you can see, this can move and then as soon as these truss elements are on the same line, they can basically, there is an axial force that is different from zero. And then this is in the two directions, because if we apply a fire scenario that with some heating and cooling, of course, the thermal joint can close, but then can also reopen. Here, there is a validation of these, let's say, gap elements with respect to OpenSea software. OpenSea software, you may be, familiar with this software, because you can also model some multi-hazard analysis between, for example, fire and seismic. And here, the comparison is really, really good. So as soon here, there is the horizontal displacement when there is this gap that is closed. You can see that there is no displacement anymore, but then there is an increase of the forces inside the structure. So the nominal curves that we used in our analysis were different. The tool that can be more relevant to this case, the hydrocarbon curve, but also the Stoddard curve that was derived from an actual accident that happened more than 20 years ago for a railway accident. And then you can see that it is there is some heating, then there is a part with a plateau, and then there is a cooling phase. You may notice here the comparison with also the hydrocarbon curves and the Stoddard curve. So there is a lower thermal gradient at the beginning, but then higher temperatures. So here there are the different fire scenarios when the fire is underneath the bridge. So when for example, road accident occurs in the motorway. So we consider some, of course, some full heating, which is unlikely. I mean, the total 65 meters is not very likely to occur. It could be more localized. So we consider also half of the bridge that was also moved from just the left middle side to the center, and also we consider some quarters in order to be more localized and probably more realistic in terms of the fire scenario. Here there is some animations. So the results are from SAFIR, but we developed in MATLAB some routines in order to produce some animated some animations in order to improve, I would say, the representation of what happened in the structure. So here you can see there is the horizontal displacement of the deck. This is under the scenario of the Stoddard curve when it is applied in the middle quarter. So you can see that there is the gap that is closed. And then if I start again the simulation, you can see that there is in the tide arch, there is tension in the deck, but then as soon as there is the closure of the thermal expansion, so you might have compression because of the direct induction. Here, there was a collapse of the bridge after 14 minutes. Here you can see the evolution, for example, of the horizontal displacement for the fire scenarios. Of course, with when is the full heating underneath the bridge, of course, the increase of horizontal displacement is higher. Here you can see that there are some, let's say, waves, but because, of course, since the heating of the bridge is not uniform, you have that the center of gravity of the bridge, moves towards the colder parts, and of course there is, but the resultant of the axial load in the deck is always applied in that point in the node line. So we might have also some eccentricities. This is the reason why you have some weight. Here, these are the representations of the results for the different fire scenarios. Above all, for the standard, there was always the collapse, whereas by applying the hydrocarbon, I mean, when it was the quarters, I mean, the collapse didn't occur, and then there was some residual deflection that also has to be quantified in order to judge if the bridge can be functional or not. Here there are some scenarios above the bridge, because of course the arch is a load-bearing member, and here there are some fire scenarios with the full arch and the hangers that are heated, or just quarters and the position. Here, for example, I think this is the simulation. Here, the problem, we introduced also some imperfections in the hangers, and the problems was that the loss of bearing capacity of the hangers because of their slenderness, that could not, being able to support the bridge with the arch. And so this is the reason why for all the fire scenarios that we simulated with the nominal curves, we found that there were some collapse. Then we applied also some FDS analysis. So we used FDS in order to simulate the fire scenario of a tanker that burns underneath the bridge. It was modeled in FDS, and then the thermal analysis and the structural analysis were performed in SAFIR. Here we used as heat release rate curves that we found in the literature, here in particular in the handbook of fire protection engineering. Here it is a quite large fire, because the peak of the heat release rate is more than 200 megawatts. It is you can find this table in the handbook that is there, and then it was used to simulate really large fires in this case. Here there was the mesh de-energetization of the computational domain. We performed a mesh sensitivity analysis in order to be time efficient, but also in terms of accuracy. And then also the mesh dimension criteria was based on the characteristic diameter that is based on the heat release rate of the fire. Here, the devices that were used were adiabatic surface temperatures gas phase devices. There were almost 2,500 on the bridge that were then post-processed and then applied in SAFIR. Here, there is the analysis of this case by using some natural fire curves with FDS. What was observed that the bridge withstood the whole length of the fire. So of course there were some localized deformation, and then very hot temperatures in very low localized parts. But the loss of stiffness and strength of that part was not sufficient enough, I mean, to collapse for the bridge to fail, and then there could be like some redistribution. Also because the arch was basically formed. Here there are the results of two fire scenarios, the one that I've just shown with the track in the middle and then also on the lateral part. And you can see there is the reflection that is 15 centimeters. Also in this case, we have to judge if this displacement that can be also very localized in some parts of the bridge is high enough to close or to hinder the functionality of the bridge. Here it is quickly, because these are work in progress of the steel concrete plated girder bridge. Here some pictures about it. Here we started with a 3D beam model, and then we are developing also a 3D beam plus shell for the concrete slab, and then also we are modeling also a totally shell model in order to account of the possible local buckling in the girders. Here are the materials that we used. We used always for the concrete with explicit creep model. And here there is one of the 5 scenarios that we applied is just on the lateral part of the bridge. The modeling of the boundary conditions were the same. So with this, let's say gap element that was made into SAFIR here, for our example, under the standard curve that was here at the left quarter. After 16 minutes, failure was detected of the bridge, the civil supported bridge. Here it is the shell plus beam model element. Here there was more refined because there are also some transfers beams into a deck, so it could better represent also the behavior of the bridge. And here there are the first analysis. For example, here there is the first comparison of the vertical displacement between the beam model and the beam shell model. In this case, we got a really very similar results. Here I put the computational time. For example, it can be also interesting. Is more than 4 hours. For this case, and for the beam, only beam is 32 minutes. So you can see that if at the end of the day we can demonstrate that the results are pretty much the same for the 5 scenarios of interest, and we could also judge on the time. For example, for the FDS analysis, the FDS analysis lasted 4 days. Okay, so which is quite reasonable still for this kind of analysis. Here there are some conclusions. So fire, as I said at the beginning, is a low probability but high consequence event. Typically in the codes, there is no provision in terms of fire safety. So typically they are not fire protected, or no measure in order against fire is taken. Typically, there are fast heating rates, high temperatures within the first few minutes. So what we did also, comparing some modeling techniques, we included the modeling of the expansion joint with this gap, and then we performed some analysis with nominal curves and natural fire curves by means of CFD modeling. Here, at the end of the CFD modeling and the thermomechanical analysis, we detected the small residual deformations, but they can be very localized. So it is also a matter of discussion how to judge the functionality. Here there are the future perspectives. So here there is the orthotropic deck model with shell elements. The tricky thing in SAFIR that there is at the moment no cavity allowed for that. So the post-processing of this is in order to apply consistent thermal analysis. For example, for the beam analysis can be really heavy. And then also, as I said, there was the total shell model for the plated girder bridge. And then we will analyze other 5 scenarios. I would like to acknowledge my postdoc, Patrick Covey, that the animations, all the analyses were made thanks also, of course, of his support, and also some master students that participate in this research project, and biggest supporters as well. So thank you very much, and then I'm available for questions.
Thank you very much, Nicola. Really excellent presentation and very impressive range of studies and range of applications with SAFIR. Very nice to see that. There were a few questions, and congratulations in the comments, notably considering you showed several tools that are really nice. So maybe the first question I want to ask you about the FDS SAFIR interfacing. Yes. So you mentioned large number of AST sensors. So I assume you did not use the so-called interface for that case, but
yes, exactly. So we didn't use it. So as you know, I was part of the development at the beginning of this interface. At this stage, that interface was mainly conceived when the structure is not included into the CFD modeling, so or the structure does not influence a lot the file dynamics. In this case, to start with, we wanted, to include the bridge inside the analysis, and then we wanted afterwards, based also on your work, comparisons that you did in the recent years, to check what is the difference by applying the SAFIR, the FDS SAFIR interface that is included into SAFIR and FDS, but also the strategy that we used in this modeling. That is, of course, more. There is more burden in terms of post-processing, because of course you take all the measurements, and then you have to put into SAFIR. So this is a large, quite a large part of the work.
Thank you. Yeah, no, that makes sense for that application, and yeah, of course you know very well the interface since you wrote most of it. And okay, so here you use the AST, but did you write a code then to handle those 2500?
Yes. So yes. So Patrick, I'm lucky because Patrick is not only a structural engineer, but also likes a lot IT. So he's very good at it. Also in the animations. So full credit to him, because he used all the outputs of SAFIR in order to create these animations for the outputs in MATLAB.
Yes, Ruben had a question about that as well. So you showed some very nice post-processing with MATLAB, some things that are presented differently than Diamond. Sometimes seemed very efficient and nice. Is that your MATLAB code? It's a little bit technical, but was it very specific to those files, and did you have to develop it specifically for that example, or is it more universal? You can read
we use for many applications for other research projects, so I think it can be adapted. This is quite technical. I know that Patrick is also in the audience. Patrick, if you want to answer to this question, you are more into this MATLAB code.
Yes, hello everyone. So it's more general, because you can use also, for example, the result of OpenSys. So I develop as general as possible. So there are some if else switches, and you can use the result of the OpenSys, SAFIR with beam element or shell element. So it's more general.
Great, excellent. Thank you, Patrick. So reaching the time, there was maybe a couple more questions in the chat if you get the chance to have a look. But again, thank you very much, Nicola, for the presentation. Very impressive, very nice. It's nice also to see SAFIR being used for bridge fires problems, because indeed that's an important problem for which, as you said, there is no standard provision, so we need structural fire engineering. Great.
Thank you very much again for the invitation. Thank you very much.